Alright, so welcome to this video. We are going to solve section B of chemistry 1000, okay, or chemistry 1000 2024 exam. So that's what we are going to solve in this lesson here. Alright, so we start with the questions right away. So question 1, they're saying cyclobutene has the empirical formula CH2, okay, and then they're saying its molar mass is 42 grams. What is the molecular formula? Okay, so how can we find the molecular formula of cyclobutene? Okay, so we know that the molecular formula is just equals to the empirical formula multiplied by n. Okay, so this n here is the factor that you find, okay, by dividing the molecular formula mass divided by the empirical formula mass. Okay, so where do we get this molecular formula mass? Okay, the molecular formula mass is the same as the molar mass. Okay, and then this empirical formula mass, we just add the molar masses in the the empirical formula. So the empirical formula that we've been given here is this CH2. So we are going to add the molar masses of carbon, okay, to the molar masses of 2 multiplied by the hydrogen there. Right, so let's add. So it will be 12.01, which is the molar mass of carbon, plus 2 multiplied by 1.01, which is the molar mass of hydrogen. So when we multiply that, what do we get? We get 14.0, and then that will be 3. Okay, so grams per mole. So this here will be our empirical formula mass, and then we've been told that the molecular formula mass or the molar mass is just what? 42. So it means we can now find this n here, which we are calling as a factor. So we are going to say n is equals to the molecular formula mass, which is 42, then we are going to divide by the empirical formula mass, which is 14.02. okay, so once we divide those, what are we going to have? What are we going to have there? Okay, so let me punch that on my calculator. So I have 42 divided by 14.02. Okay, so I'm going to get 2.9935851,746. So we can round off this. Okay, we can round it off. It will just be what? 3. Alright, so that is the factor, the 3 there. So now to find the molecular formula, we're going to say molecular formula is equals to the empirical formula, which is CH2, and then multiplied by the factor there, which is 3. Okay, so when you multiply this empirical formula by 3, we're going to get C3 and then H6. Okay, so this here will be our what? Molecular formula. So any questions there? Any questions there before we go to question 2?
No.
All right, let's go to question 2 then.
This is when I just joined the very bad network. My network was very bad. So I just have one question.
Yes, you can ask.
You got the 42 from the question?
Yes, the 42 we got it from the question. That's the molar mass. So we said the molar mass is the same as the molecular formula mass.
Okay.
Yes. So that's where we got it. We got it from the question, and then we divide by the empirical formula mass.
Okay, so you got the lowest number?
Huh?
After doing 12.01 plus 2 multiplied by 1.01, which gave you 14.03 grams per mole.
Yes.
That's the number that you divided with 42?
Yes.
Okay.
Alright, so we are dividing this empirical formula mass, okay, by adding the molar masses of C and 2 of the hydrogens, and then once we get this total, we're going to use it to find this factor here. So the factor here, which we are referring to as N, we just divide the molecular formula mass, which is the same as the molar mass given in the question, okay, and then we divide by the empirical formula mass that we found here. We're going to find 2.999, and then that one we round it off, is just going to give us 3, and then that 3 we multiply it by the empirical formula in order to get the molecular formula there. Right, so now let's look at question 2. So be free if you want to ask a question, okay, be free to ask. Alright, so question 2, B2, they're saying 90 grams, okay, of iron 3 chloride reacts with 52.0 grams of hydrogen sulfide. Okay, what is the limiting reactant? Okay, so it means here we have to know the products. Okay, once this iron 3 chloride, okay, once it reacts with the hydrogen sulfide, what are the products? Okay, all right, so we are going to say that iron 3 chloride, okay, when I add it to the hydrogen sulfide like this, okay, the products that I'm going to get will be the following. Okay, the products will be the product will be iron 2 chloride plus hydrochloric acid plus S. Okay, so these are the products that you get when these two here react. Okay, so how can we find the limiting reactant? Okay, we would have to find the moles of this guy. Okay, we also have to find the moles of this guy, and then we can pick any product here. Okay, we can pick any product that we want here. So we're going to be using the molar ratios of the reactants to the molar ratios of the products. So once you get the moles of iron 3 chloride, you're going to get its mole ratio, okay, and then compare it to any one of the products here that you want. Okay, and then we're also going to get this guy here and compare it to the product of any one of the product that we want. Okay, so if I compare this first reactant, okay, to a certain product, okay, if I use more ratios there, I'm going to calculate the amount of product that is obtained if I use this iron 3 chloride. I can also use the hydrogen sulfide to find the amount of product that will be produced if I use the sulfide. Okay, and then once you get those two products, you are going to choose the one that gives us the less product to be the limiting reactant. Okay, so that's one way of finding the limiting reactant. Or if you want, you can just find the moles of the reactant. Okay, even this one, you also find the moles of the reactants, and then you compare their molar ratios. Okay, so we are going to use the one for the products here. Okay, we're going to use the one for the products. So for you to use the one for the product, it means you have to balance your chemical equation. So how can we balance this chemical equation? We're going to add a 2 here. We're going to add a 3 there. Okay, we're going to add a 2 there and a 6 here. And then it will be a balanced chemical equation. So now let's find the moles, okay, of iron 3 chloride. Okay, so iron 3 chloride, we've been given that it's 90 grams. So what is the molar mass? Okay, molar mass of iron 3 chloride. Okay, so you go on your periodic table, you add the mass of iron plus 3 times the mass of chlorine. Okay, so you should be able to get a number that is approximately 162.2 grams per mole. So this is the molar mass of this. What about the molar mass of hydrogen sulfide here? So when you go on your periodic table, you add the mass of sulfur plus 2 the mass of hydrogen. Okay, I'm getting approximately 34.1 grams per mole. So now I have the mass of this and its molar mass. Even this one here I have the mass and the molar mass. So I can use those to find the moles, right? So we're going to say moles of iron 3 chloride is going to be equals to the mass, which is 90, divided by the molar mass, which is 162.2. So when I divide this, what am I going to get? Okay, I'm going to get 0.555 moles. Okay, so these are the moles of iron 3 chloride. So what are the moles of hydrogen sulfide there? So we're going to say moles of hydrogen sulfide here will just be equals to the mass, which is 52.0, divided by its molar mass, which is 34.1. Okay, so let me punch this on my calculator. I'm getting approximately 1.525. Okay, I can end it here, and then these are my what? Moles. Okay, so now you see that we have the moles of iron chloride, iron 3 chloride, and then we also have the moles of hydrogen sulfide here. Okay, so we can pick any products on the other side here to compare to. Okay, we can pick sulfur, we can pick this, we can pick that. So the one that is simple here to use is the sulfur here. Okay, so let's pick sulfur, okay, as our product. So let's clean this up here on top. So from the balanced chemical equation there, we see that the molar ratio of iron 3 chloride to the sulfur there, okay, will just be okay, I forgot to put a 3 there on the sulfur because it's not balanced like this. I forgot to put a 3 here because we had the 3 sulfur here. Okay, all right, so the molar ratio of this iron 3 chloride to the sulfur here, okay, will just be 2 to 3. Okay, so meaning if I have these moles of iron 3 chloride, what will be the moles of sulfur? So I'm going to say 0.555 dot x. So we can cross multiply. So it means I have 2x multiplied by 3 multiplied by 0.555. Okay, so it means our x will just be equals to 3 multiplied by 0.555 divided by what? 2. So we go on our calculator, we calculate that value. So we are going to have 3 multiplied by 0.555, and then we are dividing by 2. So when I do that, I'm getting this 0.8325 moles. Okay, now these moles are moles of what? Of sulfur that are produced. Okay, so from the 90 grams of iron 3 chloride, we are getting this amount of moles of sulfur. Okay, what about from the 52 grams of hydrogen sulfate? How many moles are we going to get for this sulfur? So we see that the mole ratio here is just 3 to 3. Okay, the mole ratio there and the mole ratio there are the same. So the mole ratio is 3 to what? To 3. So it means the moles of this here and the moles of this are just equal, because 3 to 3 it simply means 1 to 1, right? Okay, so it means the moles of hydrogen sulfide that we found, which were here, okay, are the same as the moles of sulfur. So we're going to say moles of sulfur from the hydrogen sulfide will just be 1.525 moles, like that. Okay, so now you compare which which reactant gave us the fewest number of moles. Okay, so that product that will give us the fewest number of moles will be our limiting reactant. Okay, so from the FeCl3 we are getting these moles, and then from the H2S we are getting these moles. So we see that the one that gives us the least amount of moles is just what? This here. These are the least the least amount of moles, okay, if we compare them to these ones here. So it means our limiting reactant there will be what? Will be this guy here. Okay, so we can now conclude that the limiting reactant, okay, we can say our limiting reactant will just simply be FeCl3. All right, so any questions there on how we found the answer? Any questions there?
Sir, do you mind repeating how you got that part where it's 3 to 3 on the ratio? I didn't really understand how you went about on the calculations.
Okay, so I had this. Let me take it back to the equation. Okay, so we had this equation here. So this here is the balanced chemical equation. Let me erase some of these things. So from this balanced chemical equation, okay, what is the ratio of the hydrogen sulfide to the sulfur there? What is the ratio? So we can see that in front of the sulfur there, okay, in front of this sulfur here, we can see that we have a what? A 3 here. We have a 3 here in front of the sulfur, and then in front of this H2S we also have a 3. So we are getting a ratio of this guy to this guy. So we are getting 3 and 3 there. Okay, so this is the 3 and 3 I wrote here. And then since it's 3 to 3, it means we can divide both sides by 3. We are going to get 1 to 1. So meaning that the moles of hydrogen sulfide here are the same as the moles of sulfur there. Have you seen where we got the 3 and the 3?
Yes.
All right. So now let's look at question number 3. Okay, so question number 3, they're saying calculate the density of gaseous hydrogen at a pressure of 1.32 atmospheres and the temperature of 218.7 K. Okay, so let's get what we have. So we have gaseous hydrogen, which is H2, and then we have a pressure of 1.32 atm, and then we have a temperature, okay, of 218.7 K. So how can we calculate the density given this formula? Okay, so remember when we go to the ideal gas law. Okay, so the ideal gas law or the ideal gas equation is given as pressure multiplied by volume is equals to N multiplied by R multiplied by T. So this N here represents the number of what? Moles. And then this R there, okay, it's just the universal gas constant. And then T will be the temperature, P will be the pressure, V will be the volume. Okay, so we are going to manipulate this formula here to put it in terms of density. Okay, so we know that this N is moles. Okay, so we know that moles is just equals to what? Mass over molar mass. Okay, so we're going to represent the molar mass by the capital letter and then mass by a small letter there. Okay, so we know that mass is equals to, moles here is equals to mass over molar mass. Okay, so where there's N there, I'm going to put mass over molar mass. Okay, I'm going to put mass over molar mass. So let's rewrite this formula. So we have P multiplied by V is equals to, where there's N, I'm putting mass over molar mass, then multiplied by, okay, this one has to be different from the one on top. Okay, like that. And then we multiply by R multiplied by what? T. So from this, what are we going to do? Okay, we're going to do a cross multiplication. So cross multiplication here will give us P multiplied by V, okay, multiplied by the molar mass is equals to mass multiplied by R multiplied by T. Okay, and then from here we want to find density. Remember, density is given by what? Mass over volume. So we want to manipulate this formula such that we have a mass over volume somewhere. So what are we going to do? We are first of all going to divide by V both sides. Okay, we divide by V both sides. So it means the V here and the V will go. We're going to remain with the pressure multiplied by molar mass is equals to, okay, mass multiplied by R multiplied by T divided by V. Alright, so we want to isolate the M over V. So what are we going to do? Okay, we are going to multiply by 1 over RT. So if we multiply by 1 over RT on the right hand side here, we're just going to remain with M divided by V. And then here, okay, it will be pressure multiplied by molar mass divided by RT. So this is the formula that we are going to be using in order to find the density. So we see that whatever we have on the right hand side here is the one that represents what? Density, because density is equals to mass over volume. So now we can use that formula to find the density of this gaseous hydrogen. Okay, so we're going to use that formula there. Alright, so let's use that formula. So that formula, we are saying density is just equals to P multiplied by M divided by R multiplied by T. So this R, I said, is the universal gas constant, right? So R is given as 0.08206. So that's the value for R. It's a constant. You are always given in your question paper on the cover. Okay, and then here we're going to say the pressure. So the pressure, okay, is given as 1.32 multiplied by the molar mass. So now we are considering gaseous hydrogen there. So what is the molar mass of gaseous hydrogen? Okay, so the molar mass of hydrogen is just 1.01, and then I can see we have a 2 there. So we're going to multiply this by 2. So we're going to have what? 2.02. So this will be the molar mass of this gaseous hydrogen. So I'm going to multiply by 2.02, and then I'm going to divide by the gas constant, which is 0.08206, multiplied by the temperature. Okay, the temperature is 218.7. Alright, and then we go on our calculator and then simply punch in that value. Okay, so let's go on our calculators. So if I go on my calculator, I'm going to write 3.32 multiplied by 2.02, and then divided by, I have 0.08206 multiplied by 218.7. Okay, so when I multiply and divide those, I'm getting 0.14857747489. So we can round this off to 3 significant figures. It will just be 0.149. Okay, and then the units for density are what? Grams per liter. Okay, this will be grams per liter, because the volume, the units of volume from this gas constant here, the units of this gas constant are liter multiplied by atmospheres and then divided by kelvins per mole. So from this here we're going to get the liter, so it will be grams per liter. Alright, so that's how we can find the density there. So any questions there? Alright, no questions. I'll move to number 4 then. So number 4, we are writing electronic configuration of chromium. So chromium is an exception to the general rules that we use in order to write an electronic configuration. Okay, so for us to write the electronic configuration of this, we have to know the orbitals to use. Okay, we have to fill in the 1s, and then we also have to fill in the 2s, and then from the 2s we go to the 2p. From the 2p we go to the 3s. From the 3s we go to the 3p, and then we go to the 3d. From the 3d we go back to the 4s, 3p, 4d. Okay, after 4d, what comes there? To be the 4f, and then we have I think that's all. Okay, because lithium is in the 4th period, so we cannot go into the 5th period there. Okay, all right, so these are the electronic orbitals that will fill. Okay, some of them, we won't fill all of them. So we are going to say, since chromium has 24 electrons, let's start filling these electrons into those orbitals. So we have to know that the s1, the s orbital, takes only 2. electrons. The p orbital takes only 6, the d takes only 10, the f takes 14. So we are going to start arranging them. So we are going to be using this diagram like that. Okay, so we are first of all going to fill the 1s with 2 orbitals, and then we go to the 2s. Okay, the s has 2, and then we go like that. Okay, so we follow this arrow. So from the 2s we go where the arrow is starting, which is the what? The 2p. So the p takes 6 electrons, and then we go to the 3s, it takes 2. Okay, and then this arrow will come now from the 3p to the 4s like that. So it will be 3p, which takes 6 electrons. Okay, and then we have the 4s, which takes 2 electrons. Okay, so before we proceed, let's count how many we have. So we have 2, 4, 6. So this is 10 here, and then 2, 6, 4. This is 10 again. So we are remaining with what? 4 electrons. So those 4 electrons, we are going to put them in the next orbit. So the next orbit will be 3d to 4p. So we are coming from the 3d and then we are going to the 4p. So it means here I'm going to write 3d. And 3d takes up to 10 electrons, but we are remaining with 4. So we are going to put those 4 here. Okay, so now this here, what I've drawn here, is the normal way of assigning electronic configuration for any other atom. So if it was any other atom, we would have completed our electronic configuration just here. Okay, but since it's chromium, chromium is an exception to the general rule. Even copper is an exception to the general rule. So I remember in section A we did the one for the copper, right? Okay, so what happens is, let's take a look at these two last orbitals there. So we have the 4s orbital. Okay, so the 4s, we are going to draw it like that, and then we have the 3d. So the 3d has 5 sub orbitals. So we have 1, 2, 3, 4, 5. So let's put the electrons into these orbitals. So for the 4s, we're going to have 2 electrons like that, and then in the 3d we have 4 electrons. So we have to arrange those electrons, okay, singly before we pair them like that. 4. So what we notice is that we have an empty orbital at the end here. Okay, so the general rule when it comes to electrons is that electrons don't want to pair with each other because they have the same charge. Okay, so they don't want to pair with any other electron. So we have a free orbital here. Okay, but here we have this orbital where you have 2 electrons that are pairing. So what will happen in this case? 1 electrons will move away from this here. Okay, it will go and seek freedom. So it will come and it will be in this subshell like that. Okay, so it means in the first 4s there, we're going to remain with what? 1 electron like that. So this electronic configuration that I've written, okay, where I have 1 electron in the 4s is more stable than the first one that I drew, where I had 2 electrons in here. Okay, so that one there is more stable. Right, so when the electron moves and goes and fills the empty suborbital in the 3d, okay, it means the configuration here on the 2 and here on the 4 is going to change. Okay, so what will happen there? Okay, it's going to change. So it means in the 4s now, okay, in the 4s we are going to have 1 electron, and then in the 3d we are going to have how many? 5. Okay, so this now is the one that is considered as the correct electronic configuration for chromium. All right, so any questions there?
Sir, do you mind repeating how you moved the electron from, like there where it says 4s1, and how you made the 3d to be 5, the electrons there?
Okay, so remember the original configuration that we had. Okay, so the original configuration that we had when we just did the normal steps that we should follow in finding this electronic configuration, we said we had 4s here with a 2, and then we had 3d with a 4 here. So this is the normal way of arranging the electronic configuration, but we are saying chromium is an exception to the normal way. So in the normal way, it means here in the first 4s orbital we're going to have 2 electrons like that, right? And then here it means we are not going to have that electron there. Okay, so the general trend when you have these these suborbitals. Okay, the general trend is that they don't want to have two electrons that are pairing like that. Okay, so there are going to be some electronic repulsion between this electron and this electron. Okay, so what will happen is that one of these electrons will be forced to move away from this orbital, and it will go and occupy this empty orbital here. Okay, so it will move here. So what will remain is let me get an erase. So what will remain here will just be one electron like that. Okay, so when in the 4s now we have one electron, it means even here we should change. Okay, since we had 2 there, we're going to have 1, and then there, since we had 5, since we had 4, we're going to have 5, and then here we're going to have 1. So that's how we found the 1 and 5 there.
All right.
Okay, so if you want here I'm just explaining for you to understand. Okay, but if you want, just memorize the electronic configuration for chromium and copper, because those two are special. Okay, so just memorize those two, and then for the others you can be following the rules. All right, so let's go to the next question now. Okay, so the next question, what is it saying? Okay, so we are looking at question number 5 here. They are saying consider the isoelectronic series O to the power 2 minus F to the power minus N to the power positive 1, and then Mg to the power positive 2. Okay, the question is arrange these ions in order of increasing ionic radius. Okay, so this question is very simple, guys. Okay, for isoelectronic series, okay, or we say for ions, okay, for ions the ionic radius, okay, decreases with an increase in the nuclear charge. Okay, so we are going to say ionic radius, okay, this ionic radius decreases with the increase in the charge. Okay, it decreases with the increase in the charge. So what does this mean? Okay, it means that the species or the ions with a greater, okay, positive charge will have a smaller radius, and then the anions, okay, with a greater negative charge will have the largest radius. Okay, so we can state this rule again. We are saying for isoelectronic series, okay, the ionic radius decreases with the increase with the what did I write here now? With the increase in nuclear charge. Okay, I forgot to put the nuclear charge here. So meaning those ions with a positive charge, okay, those ions with a greater positive charge will have the smallest ionic radius, and then those ions with a greater negative charge will have the biggest ionic what radius. So here they're saying we arrange them in what increasing order. So we start with the smallest, okay, and then going to the what the largest. So the smallest will be that ion that has the greatest what positive ion. Okay, so the one with the greatest positive ion there is just the magnesium 2 plus. Okay, and then we're going to say this is less than, and then the next one will be the one with the positive 1 there, and then the next one will be from there we are going to have the F minus, and then the largest will be the oxygen with the 2 minus. Okay, so you can see that the smallest is the one with the biggest positive charge, and then the largest is the one with the biggest negative what charge. So we have arranged them in increasing order like that. All right, so any questions there? Any questions there, guys? Okay, let's look at question number 6 then. Okay, so question number 6, what is it stating? Okay, so question number 6, they're saying given the standard electrode potentials. Okay, so here we have potassium ions that have been reduced to potassium as minus 2.93 volts, here we have silver that is being reduced to silver ions that is being uh, reduced to silver metal, and then it has 0.0 volts. And then here we have Hg2 plus, which is being reduced to Hg, so this is mercury, it has 0.79 volts. And then here we have magnesium 2 plus being reduced to magnesium metal, which has minus 3.7 volts. And then here we have chromium 3 plus being reduced to the chromium, which has minus 0.4 volts. So the question now is, arrange the highlighted metals in their increasing order of reducing power. Okay, so we first have to know what the reducing power is. So the reducing power, okay, the reducing power of the reducing power of a metal, okay, refers to its ability, okay, to its ability to donate electrons. Okay, so this is what we'll be referring to as the reducing power. So its ability to donate electrons is what we refer to as the reducing power. Okay, so metals with a more negative standard electrode potential, okay, are stronger reducing agents because they are more likely to lose electrons. Okay, so I'll repeat that. Metals with more negative standard electrode potentials are stronger reducing agents because they are more likely to lose electrons. Okay, so from the values that we've been given there, okay, from the values that we've been given there, let's arrange them. Okay, from the values that we've been given, okay, so metals with more positive electrodes, okay, so uh, um, I said metals with more negative electrode potentials are stronger, right? Okay, so it means metals with more positive electrode potentials are weaker. Okay, so if we start arranging these in increasing order, we are going to start with those metals that have a more positive electrode potential, and then we'll be reducing like that to going towards the negative. So the one with the lowest reducing power there will be the one with the highest uh, uh, standard electrode potential. So the one with the highest is this guy here. We can see the 0.8 is the highest. So we're going to say, okay, we're going to say silver is the highest, and then this silver will be, okay, less than, okay, the one that will follow will be the one that has a slight smaller value than the standard electrode potential for silver. So this is 0.8, the one that will follow is the 0.9. So for the 0.9, that will be the mercury, and then this mercury less than, okay, which one will follow there? So I have this minus, I have that minus, I have that minus. So which one of those minuses is more positive? Okay, so the minus 0.74 there, okay, is more positive than the others. So I'm going to say that electronic potential is for chromium. So I'm going to write chromium and then less than. Okay, so we are remaining with the magnesium here and potassium. So which one has a more positive value there? We see that the magnesium has a more positive value, okay, because it's less negative. So we're going to write magnesium here, and then less than the last one, which will just be potassium. Okay, so the way I've written them here, this is the order. Okay, so this here is arranged in increasing order of reducing potential. So this one here, the potassium, it has the largest negative electrode potential, so meaning it's the most powerful it's the most powerful reducing agent. Okay, and then followed by the magnesium, followed by the chromium, followed by the mercury, and finally the silver will be the last one. So this here is increasing order of the reducing potential. All right, so any questions there? All right, so let's solve the next one then. So the next one is what question now? Okay, so the next one is this question here. Okay, so they are saying match the given boiling points to the given hydrocarbons. So we have two hydrocarbons here. We have N-pentane and we have neopentane. Okay, so what can we notice in their structures? Okay, this one here is not branched. Okay, it starts in a linear form like that. Okay, but when we look at neopentane, it is branched. We have this branch, this branch, this branch, this branch. Okay, so the trend with hydrocarbons is that, okay, the boiling point decreases, okay, with the branching. So the one molecule that is more branched will have a less boiling point. Okay, so here we've been given two boiling points, this one and this one here. Okay, so this one here is not branched, so it means its boiling point will be higher, but this one here, neopentane, is branched, so its boiling point will be what? Lower. So we're going to say neopentane will get the 9.5 degrees Celsius, and then N-pentane will get the 36.2 degrees Celsius, like that. Okay, so any questions there? I'm pretty sure this is very simple, right? Any questions there? You are free to ask. All right, so we go to question 8. So question 8 here we are saying, during a phase change from liquid to vapor, state whether the following variables would increase, decrease, or remain constant. Okay, so we are starting with enthalpy there. So will the enthalpy decrease, increase, or remain constant during a phase change? Okay, so during a phase change, it means we are changing state. Okay, so in this case, we are specifically changing state, okay, from the liquid to the what? To the vapor. Okay, so enthalpy by definition is just um, the heat content of the system. Okay, so enthalpy is just the heat content, or the amount of heat in the what? In the system. So the heat content in the system, that's the enthalpy. Okay, so if I have, let's say, this liquid here in this container like that, okay, I have the liquid here and then I'm heating it. Okay, so when it reaches at the boiling point, what will happen? Okay, all the heat that will be going into this system will be used to change the state of the liquid from the liquid form into the vapor. Okay, so it will be, the heat will be absorbed by this liquid here so that it can be used to change the state. So what happens when the liquid absorbs the heat? Okay, when the liquid absorbs the heat, it means the heat content of that system is doing what? Is increasing, because the liquid is absorbing, okay, is absorbing that heat. So the enthalpy increases, okay, when you are changing state, the enthalpy increases. What about the entropy? Okay, what happens to the entropy? So we first have to define what entropy is. Okay, so entropy is a measure of the degree of disorder or randomness in a system. Okay, so we are going to say this is the measure of randomness of a system. Okay, so what happens when you are changing state? Okay, or you are changing the phase there. Okay, what happens? So the transition from liquid to vapor results in molecules moving, okay, more freely and randomly in gaseous phase. Okay, so as they are moving randomly and more freely in gaseous state, okay, it leads to an increase in disorder. Okay, because those particles will just be moving in random like this. It moves like that, moves like that, moves like that, just like this. It will be moving in random like that. So that will be disorder. So when you have a phase change from liquid to vapor, the entropy increases. Okay, so the entropy increases, the enthalpy also what? Increases. So any question on question number 8?
So you said that the enthalpy will increase, even the entropy will increase, or you said they remain constant? I didn't get.
I said they will increase. The enthalpy will increase, even the entropy will increase. All right. Okay, so that's it for question number 8. They both increase. And then let's look at question number 9. So question number 9, now they're saying state two quantities that must be measured to establish the rate of a reaction. Okay, so rate of a reaction is equals to the concentration divided by time. Okay, so for us to find the rate, we need the time and we need the concentration. So the two quantities that must be measured are just the what? The time and the concentration. So that one is direct. Okay, you just have to measure the time and the concentration. Okay, let's solve the last question. So the last question is on what now? Okay. Okay, so the last question they're saying benzylpenicillin, which is also known as penicillin G, okay, is narrow spectrum antibiotic uh, used to treat infectious diseases. They should be diseases they are caused by a susceptible what bacteria. Okay, so in a nutshell, penicillin antibiotic that is administered. Okay, identify any two functional groups found in the penicillin G. So we've been given this diagram there as our penicillin G. So let me bring it here. Okay, let me bring it here and make it a little bit bigger like that. So this is the diagram for the penicillin what G. So they're saying identify any two functional groups. Okay, so I can see a lot of functional groups here. So the first one is this one here, which is very easy. So this one here is called what? What's the name of that functional group? Hello, what's the name of that functional groups, guys? You do not know the name of that functional group. Okay, I can also see this functional group here. Okay, so what is the name of this functional group? And I can also see this functional group here where I have an S. What is the name of this functional group? Okay, and then what else can I see here? Okay, okay, yeah, so I can see those three are functional groups, or maybe I also identified this one here. So this one here is also a functional group. Okay, so this one here is a carbonyl. Okay, that's the carbonyl functional group. This one here is a carboxylic. Okay, carboxylic group. Okay, and then that S there is called a thioester. And then this HN there is called an amide. Okay, so we have identified four functional groups there, but in the exam they just required you guys to identify one. All right, so any questions there before we close the class? Any questions, guys? All right, so we end here.
What's the answer from question 10?
Question 10, you pick any two of these answers that I've given you.
Alright.
Yes. All right, so we end here. We shall continue the revisions.